Dear classmates, welcome to the Bist lecture. In this video, we are going to introduce a second pseudo-random test pattern generator, the Cellular Automata, CA, which was proposed by Wolfram in 1984. This figure shows an example of cellular automata. In this figure, each square represents a flip-flop, and the blue square represents a linear function, FCA. FCA is a linear function of its two immediate neighbors and itself. Take the middle FCA for example. Suppose this cell is numbered I, then its left neighbor would be numbered I-1. Its right neighbor would be numbered I+1. So this FCA is a function of its left neighbor, which is Ci-1 times Si-1. Inclusive or the cell itself, which is Ci times Si, inclusive or the right neighbor, which is Ci+1 times Si+1. Please note that the coefficient Ci equals 1 means that the connection exists, otherwise Ci equals to 0. This cellular automata is called null boundary condition because both of its right and the left ends are tied to 0. The degree of this cellular automata is equal to the number of flip-flops, which is 6. Please note that the cellular automata does not have long global wires. All the wires are local connection. This makes the place and routing of cellular automata easier than LHCA. The name of a cellular automata cell is given by its FCA function. This is a kernel map of the FCA function. Each cell in this kernel map is weighted by three numbers Si-1, Si, and Si+1. For example, the A0 cell is weighted by 2 to the power of 0. A1 cell is weighted by 2 to the power of 1. And the A7 cell is weighted by 2 to the power of 7. So the name of a cell is summation I equals to 0 to 7 AI times 2 to the power of I. For example, given an FCA function equal to Si-1 inclusive for Si, we can have the following kernel map, where we have 4 circles of 1s. The name of this cell is equal to 2 to the power of 6 plus 2 to the power of 5 plus 2 to the power of 2 plus 2 to the power of 1, which is equal to 102. So this is called a rule 102 cell. Now it's time for quiz. Given this FCA function, FCA equal to Si minus 1 inclusive or Si plus 1. What's the real number of this cell? Now please pause the video and do this exercise. Okay, are you done yet? So given this function, we can fill in this kernel map as this is 0, this is 1, and this is 1, 0, 1, 0, and 0, 1. So the name of this cell will be 2 to the power of 6 plus 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 1, which is 64 plus 16 plus 8 plus 2. This is 90. So this is called a rule 90 cell. Have you got it correctly? Now we know that the rule 90 cell has this function. Similarly, we can have a rule 150 cell which has this function. We can put these two cells together to construct a 90-150 linear hybrid cellular automata, LHCA. The left and right hand sides are tied to 0, so we call it null boundary condition. This 90-150 cellular automata is a very popular structure of cellular automata because its mathematical model has been well studied. This figure shows an example 4-degree 90-150 LHCA. This cell is rule 150 because it has 3 feedbacks. This cell is rule 90 because it has only the feedback from the left cell and from the right cell. It does not have an input from the cell I itself. Similarly, this is rule 150 because it has 3 feedbacks, and this is rule 90. This table shows the state transition of the 90-150 cellular automata. Starting from the seed 1, 0, 0, 0, we can produce the next cycle. After one cycle, this bit will be 1 again, and the second bit will be 1 inclusive or 0, so it will be 1, and the third cell will be 0 inclusive or 0 inclusive or 0, so the third bit is still 0, and similarly the last bit is still 0. So after one clock cycle, the state will be 1, 1, 0, 0. And we can repeat this to generate the other states. From this table, we can see that cellular automata also generates pseudo-random patterns. If you notice, this sequence is a M sequence. Each output of this cellular automata is the same M sequence, but they are phase shifted. For example, S2 and S3 are different by one cycle. S1 and S2 are shifted by 9 cycles, and S0 and S1 are shifted by 11 cycles. Similar to LFSR, the M sequence is also periodic. Why does this cellular automata generate M sequence? This will be shown later. Now it's time for quiz. Please generate the 15th state of this cellular automata. And question 2. What is the cycle length of this cellular automata? Please pause the video and work on this problem. Okay, are you ready for the answers? 0101 is the 14th state. After one cycle, this first bit will become 1, and the second bit will be 0 inclusive or 0, which is still 0, and the third bit will be 1 inclusive or 1 inclusive or 0, which is still 0, and the last bit would be 0 inclusive or 0, so it's 0. Now we are back to the seed, which is 1000. As you can see, the cycle length of this cellular automata is 15, which is 2 to the power of 4 minus 1. This is the maximum cycle length a 4-degree cellular automata can have. So this is an M sequence. This figure shows a n-degree 90-150 LHCA. For each inclusive OR, we have one configurable coefficient where Ci equals to 1 if the feedback exists. Then this is a rule 150 cell. Ci equals to 0 if there is no such feedback. Then it is a rule 90 cell. For each cell I, there must be a feedback from the left cell, and there must be a feedback from the right cell. The feedback from itself is configurable. So FCA I is equal to the left neighbor, which is Si-1, exclusive or the right neighbor, which is Si plus 1, and the cell itself. This one is configurable. Like LFSR, we can use matrix to represent this 90-150 linear hybrid cellular automata. The left column S plus is the next state of the cellular automata. The right column S is the current state of the cellular automata. In the middle is the C matrix. For cell S0, we know that the next state of S0 is equal to S1 inclusive or C0 S0. So in the first row, we have C0 as the first element and the 1, which is the second element. Similarly, for S1, we know that the next state of S1 is equal to the left neighbor, which is S0 inclusive or S1 itself, which is C1 S1 inclusive or the right neighbor, which is S2. So in the second row, we have elements 1, C1, 1, 0, 0, 0, and so on. So we can observe that on the diagonal line of this matrix, we can have the coefficients Ci and on top of the diagonal line, we can have another diagonal line of 1. Below the diagonal line, we have another diagonal line of 1. The other triangle elements are all zeros. So this is the matrix representation of the Cellular Automata. The characteristic polynomial is equal to f lambda, which is the determinant of C, which is the middle matrix here, minus lambda I, which is the identity matrix. Now it's time for quiz again. Given this cellular automata, what is the matrix C? Question 2. What is the characteristic polynomial of this cellular automata? Please remember, you need to use modulo 2 addition in this calculation. This problem is more difficult. So now please pause your video and work on this one. Okay, now we are back to the video. Have you done the answer yet? For the first problem, we can see that on the diagonal line, we just fill in the feedback point. For 150 cell, it is 1. For 90 cell, it's a 0. So we have 1, 0, 1, 0 on this diagonal line. On top of this diagonal line, we have 3 ones. Below this diagonal line, we have 3 ones. The other elements are all 0. So this is the C matrix. Problem number 2. To work on the characteristic polynomial, we need to solve the determinant of C minus lambda I. If you solve it correctly, you would get this polynomial, x to the power of 4 plus x plus 1. Because this one is more difficult, we will explain in the following slide. If you remember, in linear algebra, the determinant of a 2 by 2 matrix is defined as AD minus BC. For a 3 by 3 matrix, it's a little bit more complicated. The determinant can be obtained by AEI, which is the diagonal line, plus BFG. If you expand the matrix in this way, you can see from this green diagonal line. And the last one is CDH. These two terms minus CEG, which is the other direction of the diagonal line, minus FHA minus IDB. So this is a 3 by 3 determinant. If we want to calculate the determinant of higher dimension, we need to perform column expansion. Suppose we want to do a column expansion with respect to the jth column of matrix A. We can follow this formula. summation Aij times Cij, where Cij is called the cofactor of Aij. The definition of Cij is minus 1 to the power of I plus j multiplied by Mij, where Mij is the determinant of A by removing the ith row and the jth column. For example, suppose we want to do a column expansion of matrix A with respect to the first column. So we just follow the formula and write this equation. In this formula, M11 is the determinant of a smaller matrix by removing the first row and the first column. So this is M11. And the second term is M21. Please notice that we have a minus 1 here because minus 1 to the power of 2 plus 1 is equal to minus 1. And the third term is M31. Here we have a plus because minus 1 to the power of 3 plus 1 is equal to positive 1. Okay, with this formula, we can now reduce the dimension of A from 3 by 3 down to 2 by 2. Now continue from our quiz. Given this matrix C, we want to calculate the characteristic polynomial. So we want to calculate the determinant of C minus lambda I, which can be written in this way. Suppose we do a column expansion with respect to the first column. We can obtain this formula. And then after a few expansion, we can obtain this polynomial. Lambda to the fourth minus 2 lambda cube minus 2 lambda squared plus 3 lambda minus 1. Please note that we are using the modular 2 arithmetic. So minus 2 is actually equal to 0. And the plus 3 is actually equal to plus 1. And the minus 1 is equal to plus 1. So now we have this characteristic polynomial, which is lambda to the fourth plus lambda plus 1. This is a primitive polynomial. So we have reached a conclusion that this cellular automata has a primitive polynomial and it can generate the M sequence. So what's the relationship between LHCA and the CA? It has been shown that if the cellular automata and the LHCA has the same irreducible characteristic polynomial, then their matrices are similar. That means we can find a vector V to perform isomorphism transformation between the cellular automata matrix and the LHCA matrix. It is totally fine if you don't understand the above statement. The only important thing you need to understand is that if a characteristic polynomial of a cellular automata is a primitive polynomial, then it can generate M sequence and the length is 2 to the power of n minus 1. Like this particular cellular automata we used in the previous slide, it has the characteristic polynomial x to the power of 4 plus x plus 1, which is a primitive polynomial, so it can generate M sequence of length 15. And the second implication is that cellular automata and LHCA of the same polynomial can generate the same bit sequence. They are different by just phase shift. This slide shows an LHCA and a cellular automata of the same characteristic polynomial, x to the power of 4 plus x plus 1. As we can see from this state transition table, we can see that the M sequence of Q3 is exactly the same as the M sequence generated by S3. The other bits are the same M sequence. They are just phase shifted. For example, Q2 and Q3 are shifted by 1 cycle. Q1 and Q2 are shifted by 1 cycle. Similarly, S1 and S2 are shifted by 9 cycles, and S0 and S1 are shifted by 11 cycles. But they are all the same M sequence. So, the pro and the con of cellular automata are shown in this slide. The advantage of cellular automata is that it provides more randomness than LHCA because it generally has larger phase shift. The second advantage is that cellular automata is potentially faster than LHCA because it has only short feedback wires, no long feedback loops. The third advantage is that cellular automata only use small inclusive OR. We don't need more than 3 input inclusive OR. However, there is one major disadvantage of cellular automata. The problem of cellular automata is that we do not have an easy design methodology to define an LHCA structure. As we have shown in our previous example, given an LHCA structure, we can find out its primitive polynomial. However, given a primitive polynomial, it's very difficult to draw the structure of the linear hybrid cellular automata. So far, there is no good methodology to construct cellular automata from the polynomial. In summary, in this video, we have introduced the cellular automata. Each cellular automata cell can be named by its function. Rule 90-150 linear hybrid cellular automata is a very popular cellular automata, and the polynomial of cellular automata can be derived from the determinant of C minus lambda I. Cellular automata is a very good test pattern generator which provides more randomness test patterns than LHCA. However, a cellular automata can be very hard to design. Thank you for watching.